All right, hello everyone. Welcome. I hope everyone can see me and hear me. Hope everyone's having a great start to the week so far. So this is a webinar that I've put together called Data Visualization in R. So today we're going to be learning about R. We'll give it maybe one more minute just for other people to join. But before we go ahead and get started and jump into learning about R, I want to tell you a little bit about myself. So my name is Victoria Crystal. I am a geologist and a paleontologist. So I do research about the Earth and about Earth history. And I use R a lot in my research to do some of my data analysis. I have two main aspects of my research. One is I look at the chemistry of rocks, so I consider myself to be a geochemist. And the second is that I look at what rocks and fossils can tell us about ancient ecosystems. So specifically, I look at the time of the dinosaurs, and I use rocks and fossils to try and figure out how many dinosaurs were roaming around the landscape, what they were eating, if they were herbivores, what plants they were eating, and then carnivores were eating those herbivorous dinosaurs. And so I have a lot of very big data sets that I work with, both looking at the geochemistry, so keeping track of all of my different rock samples and all of the different types of chemicals that make up those rocks, and then also keeping track of ecosystems and populations. And so I use R primarily for all of those data sets and for my data analysis. And one of the most important things is that when I publish my research, I have really nice graphs and charts that visually represent my data very well. So people can see that visualized data, so they can see graphs and charts with all of my data points and be able to make interpretations about it. And so that's what this is going to be focused on today, is data visualization in R and how we can use all of the tools and all of the packages within R to make really nice graphs and plots that very easily communicate what our data is trying to tell us. Sort of like how people say pictures are worth 1,000 words. We're trying to put together graphs and charts that are worth 1,000 words, so people can very easily see what that data represents. So with that, I'm going to go ahead and share my screen and get into some of our PowerPoint slides. And today I'll be jumping back and forth a little bit from PowerPoint slides, giving you information and information about R, and then going into R itself and writing some code. So please, if you have any questions or if something I'm saying doesn't make sense, put questions out there. I'll be sure to answer them as well. Oh, my computer's thinking. There we go. Okay, share screen. All right, so we'll actually start off here in our slides. So like I said, we'll be talking about data visualization with R. So here's a little roadmap of what we'll be covering today, kind of an outline roadmap so you know where we're going and I'm not just kind of talking a bunch of random stuff. So first, we'll answer the most important question, what is R? And I'll talk a little bit more about what R is, and then we'll also get to what R Studio is. So I use R and R Studio together. R Studio has a really nice interface, a lot more user-friendly than R, and so I'll get to what that is and how we can use that as well. And then I'll show you what those two interfaces look like, what R and R Studio's interface looks like. And then we'll hop over into R and we'll get to the basics of writing R code, the basics of loading packages, and I'll talk about what packages are. And then we'll do some simple statistical analyses, and then we'll get to finally the meat of it, making graphs, charts, and plots, and the actual data visualization that I'm going to focus on today. And then also I'll give a real world example of mathematical modeling using R. And this is something that we've probably all been hearing about a lot in the news and everything, is flattening this COVID-19 curve using R. So I'll show you a model that Tim Churches put together using R to model this COVID-19 curve and how to flatten it. And then finally, I have a slide with a bunch of different R resources. So things that will help you as you start to use R. And all of these slides and all of the code that we work on today, I'm going to have sent out to you through the DoSpace, and so you can have all of that information. So with that, let's get into what is R. So for those of you not familiar, R is a programming language and an open source software. So it's all completely free. I provided links to download R and RStudio in the description for this webinar, so hopefully you've done that if you're interested. And this open source software and programming language is used primarily for data manipulation, in particular large data sets, which is sort of why I turned to R. I was trying to do all of my data manipulation and graphing in Excel, and when you have hundreds of thousands of cells worth of data in Excel, it kind of slows it down and it becomes very tedious to look at that data and play with that data. And so I ended up switching over to R. R does not have a problem managing large data sets at all. So R is very, very great for data manipulation, particularly of large data sets. R is also most commonly used for statistical analyses. So typically when you hear about R, it'll be for statistical capabilities. There are a lot of statistic programs, functions written into R, and then there's a lot of other packages that you can get to R that do a lot of really great and very specific statistical analyses. But we're not going to cover that too much today. We're mostly just going to focus on this last bullet point here, the graphical display. You can do a lot with R in making very, very nice plots and graphs and interactive plots, which I'll show you with this link in just 1 second here. The other great thing about R is that it's extendable. So there's a number of commands and functions written into the R programming itself, but then it's also very, very easy to write additions to that. And so that's what we call the development of packages. So packages are just specific functions and commands that are written that you can then add into R, so it recognizes a whole new set of commands and functions. And those are really easy to do, very easy to add in. I'll show you how to install them and load them today. R is also very easily integrated with C, C++, and Fortran, which I don't personally know much about. I don't use those, but I know that people who do use those say that it's fantastic that R can easily integrate with them. And then finally, the last really great thing about R that R can do is it has a really nice document output. So you can basically take all of your code and everything that you have generated from that code and just output it into a really nice either HTML, PDF, or Word, and have everything all in one place, which is really nice. And then what is RStudio? So like I said, I use R and RStudio together. So RStudio is an integrated development environment for R. So here's a little screenshot of what the interface looks like here. So it's got a console where you can do all of your code, but then it also has this really nice organized workspace layout. So you can really easily see all of the different components of things that you just. It also has nice syntax highlighting tools, which I'll show you once we hop into the RStudio. And then it's got great tools for exporting plots and files. So you can really easily import data sets from other files and then save your plots that you generate as PDFs or as PNGs. It's very easy. And then it also generates what we call an R Markdown document, which I'll show you in a little while, but it's this very organized document that has all of your code and all of your output and then any word processing that you would like to do associated with the code and the analysis that you're doing. And RStudio, also completely free, open source. It's available for either desktop or web browser. So you can load it directly onto your desktop and work from there, or you can keep it all in a web browser. Before we jump into writing code, I just want to point out one thing, kind of a little warning, steep learning curve ahead. R does have a very, very steep learning curve, especially if you're coming from a background where you don't have any coding experience. That was how I was when I first came to R. I'd never done anything with coding. I'd only ever used Excel. And so I was very, very overwhelmed and very frustrated by everything in R and learning to code and getting the syntax of the code and everything. So just a warning, it is going to be challenging. It might get frustrating at times, but don't give up. You just have to make it past that very steep part, and then you have all of the tools and you're able to do a lot more in R. So keep at it. Don't get frustrated, even though it is kind of challenging and very frustrating. And this is something that I tell all of my students that are interested in using R, and all of my friends, anyone that I know, stick with it through that steep learning curve, and then it'll be an amazing tool that you can do so much with. So this is what the R interface itself looks like. And like I said, I don't really use R on its own. I use R with RStudio because this is just kind of one big console, and I don't really know when I type in my code where it goes or where my plots are and all of that. So I actually kind of stay away from using R on its own, but this is what it looks like if you're interested in using R by itself. And then this is RStudio. So this is what I use when I use R when I code anything. And so this just has a really nice organized interface. You can see there's 4 different windows here. I've labeled this first one. So there's window, window, window over here, and window over there. So this first one is your R Markdown window. So this is the window that I primarily do everything in. And like I said, the R Markdown is that well-organized document that has all of your work, including your code and your plots, and your text and any sort of word processing capabilities that you want with that, which is one of the fantastic things about this R Markdown function. Let's say you were working on a project for work and you had to turn in a report about this data to your boss. So instead of having your word processor open here on this side and you're typing all of your notes and writing up your report, and then you're running all of your code and processing your data and generating plots on this side, you can do both of those things together here in RStudio. And I'll show you how to do some of the word processing capabilities of RStudio. But you can do it all there, and then you get this really nice output from the R Markdown that can be either an HTML, PDF, or Word. And I'll give you an example of what that looks like in just a few minutes.
Victoria, we have a question here from Kate.
Oh, yeah.
So Kate is asking, is there any online introductory course that you would recommend for learning the R and RStudio platform?
Ooh, an online introductory course. There are a bunch. Totally spacing off the top of my head. I think, what is it, Code School, something like that has a really good one. But there's just a ton of really fantastic online resources with R, which is one of the really nice things about it being open source, is that so many people are using it that there's just a ton of online resources. I think probably most of them out there would be really good. Yeah, Code School, I think that's what it's called. That's the only one that's coming to mind, but I know there's others. So I think just do a quick Google and kind of your top hits will probably be the best. Really the great thing about using the internet with R is that any problem that you have, any code that's not working or anything you're trying to do is so Googleable. Just Google your question, or like there's a lot of forums that have like, this is my code, it's not working, why? And so there's just a ton of fantastic resources out there. I in the last slides of some nice cheat sheets for some of the code and some of the packages that we'll talk about. There's a nice resource that I have. It's called YAR, the Pirate's Guide to R. And that's a fun one. There might be a online program or an introductory course associated with that book. I'm not quite sure, but hopefully that answers your question. There's a lot of great resources out there, so I don't think you can go wrong with any of them. Please continue to ask questions if you have them along the way. That was a great question. Let's see, back to the RStudio interface. So this is our console window, so we can code in here. I prefer to put all of the code up in the R Markdown because that keeps a record of it. So you enter your code and then you can run it again and come back to it and edit it and revise it. But if you put it down in the console, it's kind of one and done. You run it and then it doesn't remember it, so to speak. You can't come back to it. So I really only use the console if there's something that I just need to run once, like installing a package or querying a command, which I'll show you. If you can't remember what something is, there's a really great help function in RStudio that'll help you remember what you need to input for it. So I do that in the console window. This window up here is the environment and the history window. So anytime you name an object or a variable or a data set, which I'll show you how to do, it'll appear up there. So not only will you be able to see it in your R Markdown file, but you'll be able to take a peek in that environment and history window and see it up there as well. And that's just a really nice way to keep everything organized. And then down here is your viewer window. So you can see any files associated with this R project. You can see your plots, you can see any packages that you've installed, and then you can also see all of your help functions in there. All right, so let's open RStudio. We'll do a quick swap-a-roo here. So here's RStudio. It's got all of our folders, all of our windows, just like I mentioned here. So this is our Markdown, this is our console, this is our environment and our history, and then this is our viewer window. So the first thing that you want to do when you open RStudio, and you can open RStudio completely independently of R, you don't have to have them both open, you do have to have them both installed and up to date to use R with RStudio. So the first thing that you'll do here is go up to File, New Project. And I'm not going to open a new project because I have all this set up to show you right now, but basically it'll ask you if you want a new directory or an existing directory. And basically directory is just referring to the folder that it's saved in. So do you want to start a new folder on your computer where all of your work from RStudio is saved, or do you want to save it in an existing folder? And so then once you do that, that folder will show up down here where you have everything associated with that R project. As you can see, I've got the R project itself, so that'll be this file that ends in .rproj, and it's got this little kind of cube logo there. And then I've got all of the files that I've generated or added to that folder to make this document. And then the next thing that you'll want to do is you'll want to do new file and then R Markdown. So again, I'm not going to do it here because I have an R Markdown file all set up to show you, but that's what you would do. And then you would give it a name and then specify where you save it within that R project. And so then up here in this window is where you would have your R Markdown. So why don't we go ahead and start looking at some stuff in the R Markdown. Typically when you open a new file, it'll have kind of some code and some writing already in there, just as like showing you this is the R Markdown. I usually just delete all of that. I don't pay attention to that. And then I just start with what I want to put in there. So like I said, one of the great things about R Markdown is that you can create a full document with all of your text and whatever you want to say about the project that you're working on in R, along with your code and all of your output and everything that you've generated. So actually, let's real quick just pull up an example. So let me show you, this is the HTML output. So this is that R Markdown output that I've put together for the class here, the webinar. So as you can see, you can change anything you want here, just like you could a word processor. So here's our heading, here's our subheading, and then here's our text. And all you have to do is put in some syntax using the keyboard functions. So similar to LaTeX, if you want something to be heading, you just use symbols to tell the program basically this is a heading. And then here we've got the rest of our HTML output from our R Markdown. So as you can see here, anything that's in code, any code that we've written is going to be in these gray boxes here. And then any output that is generated from that code is going to be in a white box immediately below. So we've got a bunch of series of codes and outputs and codes and outputs. And then as we scroll down, there's our data set output. We've got a big data set that we'll be looking at here in a little while. And then let's keep scrolling here, another data set, some more outputs. And then there we go. Now we're getting to some of our plots. So here's the code in this in this gray box here that is generating the plot. And then there's the plot below. And so you have everything together just very nicely. Here's some notes about the code, and then some more plots and everything just very nicely all put together in one document here. And you can customize this as much as you want. You can choose what you show and what you hide and things like that. So you can basically really make it your own and generate a really nice report from R Markdown. So let's get into it a little bit. So like I said, you can make headings. And so all you have to do to make a heading is just put a £sign in front of it, or a hashtag, as the kids are saying these days. And so one hashtag denotes the highest heading, and then 2 hashtags is a subheading, 3 hashtags is another subheading, and et cetera, et cetera. And then regular text you can just type out in here. So this is our Markdown, yay! Whatever you want. And then, like I said, when you do code, it is in the gray boxes. And in order to get a gray box put in, you just go up here to Insert, where you've got this little C, click the down arrow, and then you have all of these options. So you can put in code, and we call these code chunks. So you can put in code chunks in, you know, all of these. We'll pick R, since this is about data visualization with R, and there's your little code chunk. And so basically everything between these 3 little apostrophe things, which is actually the button to the left of the 1 on a keyboard, is basically telling R, okay, anything between these sets of 3 little apostrophe things, read that as code. Inside there's commands and there's functions that you need to run and produce an output for. And then everything else outside of these boxes, it's interpreting as text, kind of part of your word processing capabilities there. The other thing that you can do with these is right next to the top set of apostrophes, we have R in the little curly brackets, and that tells us that this is code in R. And so if we had picked something else, it would say that in there. And the other thing you can do is you can add a title to that. So I always title all of my code chunks so I can remember what it was that I was attempting to do with that code chunk when I come back and look at this document later on. So that's our little code chunk here. And so why don't we get into some of the code and the actual capabilities of R. And I have everything that we're gonna talk about and all the code that we're gonna look through already in here. I did a practice round of the webinar where I just typed everything out, and I think it was a little bit boring for the viewers because you would just be watching me type. So I do have everything in there that we're going to do already. So if I'm going through something a little bit too fast, or you wanna know, you know, what is this input for this command here, just stop me and let me know. So that being said, R is a programming language, so there's specific commands and functions that are written in that the program will recognize that when you type that, oh, the program has something that it has to do from that. And so I'll show you how you input those commands, but just keep that in mind as we go on, that there are commands that you put specific inputs in, and then R will recognize that as generating an output. So this is our first code chunk, yay! And so we'll just start off with the basics of what R can do. So simple arithmetic is really easy to do in R. You just type it in there and it'll do it. So I've got some really easy examples as 2 + 3, 2 × 4, but you can make it more complex. It recognizes order of operations and all of that. So you can type in whatever arithmetic stuff you want, and then to actually run this code, to make it go, you can either click on this little green arrow, kind of like a play button here on the right side of the code chunk. Keyboard shortcut, green button, or you do for a Mac, Command Enter Shift, or for a PC, Control Enter Shift. And then if you want to run just part of the code, let's say, because we've only talked about these 2 items up here, if we just want to run those, we don't want to run the whole code chunk just yet, you highlight it, and then you can either come up here where it says run and arrow down and click run selected lines, or you can do Command Enter or Control Enter for a PC. I have a Mac, so I always say Command first because that's the keyboard that I'm directly looking at. And there you go, right below our code chunk, we have our output. So 2 + 3 is on this first line of 5, and then 2 × 4 is on our next line of 8. So pretty easy to do arithmetic. R also has a lot of basic functions written into it. So for example, square root, R knows what that means, and you just have to type, if you want a square root, the command is sqrt. And once you type that, you need to specify what it is that you want the square root of. And that's how most commands in R work. You have to give the command, you want it to do something, and then you have to tell it what you want it to do that too. So for example, and this is one of the really great things about RStudio here, is that when we're hovering our mouse over that command, square root, it shows us the inputs. So in that little yellow box that shows up when we mouse over it, we see the command sqrt, and then X inside those brackets, it's telling us that X is what we need the square root of, and so that's the information that we need to input into the program. So in that bracket, I just picked a random number, 16, and then we'll highlight that and run it, and there you go. Down below, we can see our output is 4. So we got the square root of 16. One of the other cool things that is built into R is round. So if you have a really big number with a lot of digits here, big meaning lots of digits, not necessarily a large number, with a lot of digits that you want shortened, you can do this command round, and then within the brackets or parentheses, so R will call parentheses brackets. So if you accidentally mistype it, we'll pretend I left off that last bracket. Let's see, oh, we've just confused it. Here we go. If you hover over the X, so that's what happens when you get an error. It'll see unmatched opening bracket. So that's just a parentheses. So we'll go ahead and put that back in there. So this round command, you need to specify, as you can see when we're hovering over it, X, so you need to specify what it is that you need to round, and then you need to specify the number of digits. So it will default to 0, so it'll round it to the nearest whole number, but let's say we want to round it to 3, so we've got pi here and we want to round it just to get 3 digits. We can run that. Oops, what did we do here? Actually, this is a good, let me go back here. I've got a nice little error messages slide. So it's really common to get error messages in R. And primarily, the first thing to do to fix them is check your syntax. Are all of your parentheses closed? So I think what happened was I messed it up when I deleted that last parentheses. So we'll go back and we'll figure that out. But that's the most common thing, that you leave off a parentheses. And so basically some command looks like you're still trying to input information in order to get it to go. And so R is confused. Typos are really common. I make a lot of typos. So sometimes it's just that I typoed something. Maybe I wrote SQT instead of SQRT for square root. R also recognizes capitalization. So if something is supposed to be capitalized and it's not, that'll give you an error, or vice versa. Also missing any plus signs. So as you'll see, once we get into building some more complicated code, you're adding things to it. So you're doing this plus this plus this plus this. And I always forget to leave off plus signs, so that could be 2. The other thing that you can do is check the inputs for the commands. Is there something that you need to specify that you didn't? And I'll show you how to do that using the help in that little viewer window down there. We've got help. I can show you how to do that. And then, like I said, just Google the error message. The nice thing about R being open source is that there's so many people out there using it and so much information about it on the internet. So if you're having the issue, likely someone else has had the issue too. So just Google it, and usually the answer is there. All right, let's go back to R. I'm just going to run this whole chunk, and hopefully that'll get rid of it. There we go. There we go. We've got pi rounded to 3 digits there. The other thing that we can do, just kind of simple stuff, is logs. So R will recognize taking a log of something. The command is just log, and then you have to specify in that first brackets what it is you want to take the log of, and then you can also specify the base. So R's default is to default to natural log, so base E, but you can specify it to be anything. And then you can also nest commands within each other. So as you can see here, we're taking the log of 34 base 5, just random. And then that's going to give us a big decimal, and so we can also round that as well. So we can nestle that log inside the round command. So we'll run that there, and there's our result 2. So that's 2 because we didn't specify a number of digits to round to, but if we wanted to, we could even do digits equals, and as you can see, one of the nice things about RStudio is that it'll prompt you with what it thinks that you're going to say. So I typed in the first couple letters of digits, and then it popped up there, and I just hit enter, and it filled in the rest of it. So we'll do digits equals 3, and then we've confused it. So I'm just going to run this whole code again, and there we go. We've got on our next output down here, that's it, 2.191. And then the next thing we can do is getting into some simple statistics. Again, ours is most commonly known for doing statistical analyses. So getting into some of our simple statistics, mean here, we can take the mean of something. And one thing to note is that we are taking the mean of a series of numbers or a list. And so in order to get R to recognize that we want the mean of, in this situation, 1 and 2 and 3 and 4 as a list, as something combined, we need to use this C function. And so C just stands for combine or concatenate, which means everything within the parentheses, within the brackets of that C, is looked at together as a list or a vector there. And so this is just telling R that we want the mean of 1 and 2 and 3 and 4. And so we can go ahead and we can run that, and there we go, we get 2.5. So that's the mean of 1 plus 2 plus 3 plus 4 divided by 4. All right, so now let's get into kind of some of the meat of stuff, is naming objects, variables, and data frames. So let's pop back over here to this slide that I skipped over before. So we're going to talk about creating objects or variables. I'll use the term object and variable sort of interchangeably, and vectors and lists, same thing, and then data frames. So basically, creating an object or a variable is just assigning a value to a name, essentially. So I have here a word or a set of letters, because some people don't necessarily like to call it a name, that you're naming an object. But you're basically just assigning a value to something that you can then type in later on. And so instead of saying, well, here, I'll just go to the example here instead of trying to think of another one. Whoops. So here we are naming an object. So we're calling it object, and we're saying it's equal to 1. And so then instead of typing 1, we can type object. We type object into R, and it recognizes, once we've assigned the value of 1 to the term, the name object, anytime we type object, it will recognize that that means 1. And we can make things a lot more complicated, so it doesn't necessarily just equal 1 number, and you'll see that as we move along. And then vectors, we can do the same thing where we assign a list of values to a name. So here is our example, vector. We assign that 1, 2, 3, 4. And so then anytime we type vector, R will recognize it as 1, 2, 3, 4. So in that example that we just gave with mean, we could have typed mean of vector once we've assigned the value of vector 1, 2, 3, 4, and it would give us the same result. And then finally, a data frame. And so this is just assigning a data table that's organized into columns and rows of data, just assigning that a name. So here for the example, we've said data frame equals this table. And so then anytime we type data frame, it'll give us this table. And one thing to note is that R does not recognize spaces in these names. So here I've made data frame as one word. You can do data dot frame or data underscore frame if you want, but you'll get an error message if you try and name it data space frame. So let's get back into things. So here's our next code chunk. I've separated things into code chunks based on what we're doing, just to keep everything well organized, but it doesn't really matter how you organize your code chunks, that's up to you. So here's our first example. We are assigning X to be 2. And instead of using the equals sign here, we're gonna use this little less than sign, which is what is when you hit shift and comma, and then a hyphen. Because typically in the syntax of writing commands, we use the equals sign. Like when we went up here and we said digits equals 3, so we wanted to round to 3 digits, we used the equals sign here. And so when we're naming variables or lists or data frames, we use this kind of arrow-like symbol. So we'll go ahead and run that here. And then as you can see in our environment window, now that we've named something, it pops up here. And so this is just a really nice place to have everything well organized. All of your values or your lists or your data sets are all going to show up here. And so if you forget, that was 10 minutes ago, what did I name X? You can just look up here to X and see that it's 2. The other thing you can do is you can just type X and then run that code, and R will know that you mean, X equals 2, and so then it'll print 2 down here. That'll be your output. We can get a little bit more complicated here with what we name, so we can do, I'm not very creative with my name, so I just did new object is X times 3. So we can go ahead and run that, and then up here we see our new object appear with the value of 6. And then here we can get into generating some lists. So this is the same thing that we talked about when we did the mean. We are telling R that we're generating this list, which is all of these values combined. So combining them makes them the list, or concatenating them makes them the list. And so, for example, we're doing a list of temperatures. And so we're saying, okay, temperatures equals 57 and 60 and 85 all together combined. So we use this little C function. And you can make lists that are either numeric or characters. So there's 2 classes of things that you can do: numeric, which is numbers, and characters, which is text and words and things like that. So I have 2 examples here. Temperatures is our numeric list, and weathers, where we have cloudy, sunny, rainy, that's our character list. And so we can go ahead and run those, and you see them appear over here in your environment window. So there's temperatures and weathers. And then next to the values of those, the things that are actually part of the list, it'll also tell you what kind it is. So if it's numeric or if it's character, so what class it is, basically. And then it'll also tell you how many values are in it. So within these square brackets, R always does rows first and then columns. So we have 1 row of 3 numbers, of 3 kind of columns here. And so if you forget, what did I call temperatures? I can't, or what did I include in temperatures? I can't remember. You can always look up here. The other thing you can do, if you can't remember how many values, like, oh, did I track temperatures for 3 days, or was it 4? You can do this command over here, length, and then put in weathers as your input, run that, and it'll tell you 3. Same with class. If you can't remember, was weathers numeric and temperatures character, or was it vice versa? You can run this code, this command class, and then it'll tell you there, that's the character. So weathers is the one that you called cloudy, sunny, rainy. You can also add to it. So let's say like you're keeping track of the weather and then the next day it snows. So you can also very easily just change what you're calling weathers by redefining it. Weathers equals, and then again, concatenate, snowy, and then instead of retyping everything that you had before, you can just put the old weathers. So it's basically saying weathers plus snowy. And you run that. Why didn't that go? There we go. And then up here you can see we now, sorry, I ran it twice. So we have 5 values here, but that should technically be a 4. So we see the new value up there. And then we can also start doing some simple statistics of these. So temperatures was our numeric list, and so we can run that, and that'll give us our mean of temperatures. So we can start getting into doing some more sets. So R has some data sets that are already built into it. And so one of those data sets is called Faithful. And that's just data from Yellowstone, from the geyser Old Faithful in Yellowstone National Park. And so it has the time of eruption of the geyser and then the waiting time between eruptions. And so that's just kind of nice. It's built in. We can play around with that. And so here we can name our data. So we can just call on that data set that's already, that R recognizes, and we can just name that as a data, as data here, and we run that, and then up here we see data, because we just called the Faithful data set the name data, we have 272 observations with 2 variables. And if we double click, that'll actually appear up here in our Markdown window so we can see that data. So in this first column, we've got our length of eruption in minutes. And then in our second column, we have the length of waiting between eruptions. And then there's 2 ways that we can look at that data, actually technically 3. So we just clicked on it, or the second way we can run it here in this code, and we can get an output from the code to show us the data down below. So we just run the word data because we've already told R that data is this faithful data set, and it'll print it here. We can also do print data, so we can just see it printed. Those 2 work the same way. If we only want to see the first line, first couple lines, we can run head, so just like the head of the data set, and then we get the first 6 rows. So now this is where we get a little bit complicated because we can't just take the mean of a whole data set, right? That doesn't really make sense. Why would we take the mean of 2 different variables combined? And R recognizes that. So if we try and run mean data, we're going to get an error that this is not logical. It doesn't make sense to run. And so now we can start looking at some packages that we add to R to manipulate the data and change this data table and really be able to get, okay, we're not taking the mean of the whole data set, that doesn't make sense, but how can we take the mean of just the eruptions or just the waiting time? And so there are 3 packages that we use to, as I like to say, play with the data or manipulate the data inside this data table. And so these packages are dplyr. I'm not sure how you are supposed to pronounce that, but I call it Dippler. And then tidyr, I call that tidier. And then this one, magritter. And so the way that you install packages is you come up here. Oop, there we go. You come up here and you hit install packages. Then you get this little thing, and then you type in your package name, and it gives you all of these different options. So we want tidier, and there it is. And then you click on it and you hit install. This is giving me a kind of an error message because I already have it installed, so I'm not going to do that. But that's how you would install it. And then if you go over here to packages, and scroll down to tidier, there it is. And then once you've installed those, how you're going to use them, so it recognizes that it's going to see those commands from that package. And so you do that by just hitting library. So that's just a command that says kind of load the library of all of the functions in these packages. So I'm just going to run that code chunk overall. There we go. It's run. Now those are loaded. So the first thing that we have to do if we're going to start manipulating our data or playing with our data is we have to save it as a data frame. And this is kind of a little bit complicated, but saving it as a data frame really just allows us to kind of be able to pull out and separate those columns and rows. So that allows us to kind of tell R that we're going to recognize that we're going to start picking apart this data set and adding things to it or subtracting things and just playing around with it. So we just have to save it again as a data frame. And I'm just going to save this as a new name so we don't get confused, my data, and then just naming it my data as data frame. So that's a command that just changes our data set to a data frame. And then we're taking that same data set faithful. And we're going to do that. So I'm going to run that. And then up here we see we've got my data, and we still have our eruptions and our waiting. So then once we've done that, we can actually get a meaningful mean from something. So let's take the mean of just the eruptions. So if we want to see what's the average eruption length of Old Faithful, we do our mean command again, and then we're specifying of my data, but then specifically just the eruption column. And so you need to add this little $sign between the data set name and the column name. And so we can go ahead and run that. And there we go. Down below this code chunk, we get our output of about 3.5 minutes. There is our longest eruption. The other thing we can do instead of specifying the column name is that we can specify the mean of my data and then the first column. So like I said, R has within these square brackets, row then column. So we don't want the data of a row, so we leave that blank. But we keep a comma in there so we know that we're talking about column. So we want the first column, and then we just need to tell R that it's a number. So we can either look at the data in these columns as numeric or character. And so we want to make sure that we're telling it that we want it's numeric. And so we can run that, and we get our same 3.5. We can also get into doing some more statistics. So again, just simple statistics minimum. So if we want of our, let's say, waiting time, there we go, that's 43. Maximum, same thing, we can do that, and it's 5.1, that's our longest eruption time. We can take the median, there it is, 4. And then we can also do column means. So we can take the mean of all of the columns here. So we can go ahead and do that. And there we go. There's our mean of our eruptions column and our mean of our waiting column. We can also do that with rows. Necessarily, that doesn't for this data set, but if we had a data set where we wanted the means of all the rows, we could. So there we've got, you know, all 272 of them. We can also arrange the data, and so if we use this command arrange, that will order it in ascending order, so smallest to largest. And so let's just specify, we don't want to do that to the whole thing, we can just specify that we're doing that with eruptions. So we do the command arrange my data eruptions. Run that, and there you go. The smallest is 1.6, and then ascending from there. Let's say that we wanted to create a new data set just from the eruptions. So we wanted to separate out eruptions to be able to maybe plot those just by themselves or to do something else. We just create a new data set. So we're naming something, we're gonna call it my eruptions equals, and then we can do select. So select is just taking a column or a variable. And so we're selecting from my data the eruptions column. So if we run that here, over here you can see we've got my eruptions that appears, 272 observations with one variable. So if we click on that, that's just the first column. And then we can also filter the data. So let's say we're just interested in looking at observations that are greater than, eruption times that are greater than 2. So we can filter my data eruptions column greater than 2. So we'll run that, and there we go. So we're back to just using my data. So we have both of our columns still there, and here's a list of all of them that just have the eruptions greater than 2. And then let's say we wanted to save that as a data set and then be able to plot that or further manipulate that. We could save that as something else. So let's define it my new data, and then we'll just give that same command filtering my data with eruptions greater than 2. So we'll run that. And then as you can see here, we've got my new data that now has 217 observations. So it pulled out all of the eruptions that were fewer than 2 minutes. We can also rename columns or variables within this data set with the command rename. I'm gonna kind of go through this a little bit fast. I realize we're running a little bit low on time here. So here we're renaming columns. We're also adding columns. So if we wanted to add a column, we could do mutate, and then we can specify we're adding a column called total time where we're adding the 2. Or we can do mutate where we add a column and then we can use one of these if-else commands. So if eruptions are greater than 3, put yes in this new column, otherwise put no. And so we have a new column, long eruption, yes, no, yes, no. We can also create data from scratch. So that is using the command data frame. And so for this, I made a data frame, I named it data frame, and then I used the command to make a data frame. So data frame, I made variable 1, just a random sequence from 1 to 1,000, increasing by 2. And then I made variable 2, just 2 times variable 1 plus 3, something really linear. And so I did that. And then let's get into some plotting here in the last couple minutes. So Ggplot 2, because this is the meat of it, this is the important stuff. Ggplot 2 is the package that has a lot of really great plotting capabilities. Actually, let me pop back over here. I realized that I never clicked on that link that I wanted to show you, this is all of the capabilities for plotting things with Ggplot 2. So we can make some pretty basic scatter plots here. We can add arrows, we can add lines, we can make some complex marginal plots, we can change the appearance of all of these plots, we can add some stem and whisker plots, we can make histograms, we can make grids. And then let's get down into some of the really cool stuff. We can make art, so we can write code that will generate these art features here. We can make interactive plots. So here's a plot with some data. We can hover over each data point and see more information about it. Same with this heat map here. Scroll down. This is one of my favorites. We can overlay data on top of a map on Google Earth. So each of these data points is an earthquake that happened, plotted on the map in the exact location that it happened, and then you can hover over it. You can make some of, whoop, why am I zooming in here? Woo, here we go. You can make some 3D plots, and then you can make those interactive as well. So we can turn it and see the full three-dimensionality of it. Kind of same with these, we can click on each of the individual components. We can also make animations. So here's a nice animation. We'll click on this one. That we can see as time goes on, as the years go on, we can see this data grow and change. So we can do some really cool stuff with Ggplot. So let's get into actually using Ggplot here. So the command is pretty simple. I usually make a new plot, so make an object of the plot, and then you do Ggplot, what you're plotting, so the data. So this is just the data that I generated called data frame. And then you have to tell it what you want for the X and the Y coordinates. So that's aesthetics, how you want it to look. X is variable 1, Y is variable 2, and this is a line, so I'm going to specify the geometry of the plot is a line plot. So I'm just going to run this whole code, and boom, there we go. We've got our first line plot. All right, so now let's get into making some more complicated plots here in the last couple minutes. For example, I've loaded in some of my dinosaur data from a paper I published a couple years ago. So it's just kind of a fun data set to play with. So I've just called this paleo data. And then this is a nice command, read.csv, and that allows us to read in data from an Excel file. So all you have to do is save your data in an Excel file from an Excel file as a CSV, so save as CSV, in the same folder that you have your R project in, and then do this read CSV, and there we go, we've got our data. So it's got 4 different variables in it. The site, so this is a bunch of fossils that I collected. So the site is just, is it from fossil collection site 1 through 6? Then the animal, what animal is the fossil from? And then the carbon and the oxygen concentration. And we don't need to worry too much about what those numbers actually mean, but they're just comparing the carbon and the oxygen to a known value in a rock. So that's why you see some negative values. It's not that there is a negative concentration, it's just that it has less carbon than the rock. All right, so here is some of the cool stuff that we can do with Ggplot. So we're gonna make plot 2. We're gonna plot our data, so paleo data. I'm gonna make carbon the x-axis, oxygen the y-axis, and then I'm gonna plot it as a scatter plot. And then I'm going to customize it. So I'm going to change the theme. It defaults here to this black and white kind of gray theme. And then I'm going to change that. There's a ton of different options. If you just type, there's all of these different options. So we're going to do black and white because that's my favorite. Then we're going to add axis titles. So we're going to do X label and Y label, and we're going to add titles to those. We're going to title the whole plot using this GG title, and then we're going to change the theme of that title, so what it looks like. So we're going to do, we're going to make it red, size 14, and we're going to make it bold and italic. And R is built in to recognize all of these things. So you can type in red, and it'll know what red is. You can type in bold or italic, and it'll know what that is. Then I'm going to add some lines to it. We're just going to run this for time purposes here. So I've done all of these customizations, added some vertical lines, some horizontal lines, specified dashed or solid line, added random annotations here, some text. I don't know why that just highlighted. Added an arrow if you want to point to specific data points, change the color, change the size of all these different elements. It's very, very easy to customize it. All right, so now let's work on adding some variables to the plots here. So we had our just carbon and our oxygen, but let's say we want to see what site these fossils come from. So I just added a command here to color. So color code by site, and then I specified factor because I wanted just individual one, site one is one color, instead of it thinking that there's an infinite number of continuous sites from 1 to 6, like 1.1, 1.2. And so that gives us this fun plot here, where we have all of these different colors for each point where they come from, what site they come from. The other thing we can do, like we talked about earlier, we can mutate our data. So we can add a column. So let's say we want to see what the total carbon and oxygen added together is. So I just do new paleo data, mutate the old paleo data, add a column for total carbon plus oxygen. So we're going to run that here. And all of this code down here is just specifying that we want this to be red, we want that to be size 14, we want this to be blue at an angle, all of that. And so here we go. I've added another variable layer, shape is animal. So all of these different data point shapes, so these plus signs are river snails, the squares are fish, the triangles are dinosaurs, and the circles are crocodiles. And then it gives a legend over here. And you can customize how you want the legend, where you want it, what font size, all that stuff. And then I've also specified that the size of the data point is the total. So the larger the data point, the larger the total. And you can see that over here. We've got some really tiny plus signs down here, some bigger ones up here. And then you can also make different grids. Oops, scroll too far. You can make different grids. So let's say it's really complicated to have all that on one plot. But let's say we want to separate it out by by animal. So we can say, all right, this top plot is crocodile, dinosaur, fish, and river snail. And that makes it a little bit easier. You can see, you know, each animal individually instead of having to look for the different shapes. So you can do that too. You can also make it a grid in the other way, and this is, so you do the grid vertically like this using facet wrap, and then you have to specify which variable you want to facet wrap it with. And then you can do facet grid, and that just makes it a grid kind of across. And as you can see, that's a little bit easier to read than having it in columns. So you can play with it, customize it, change the size of these different grid pieces here too. You can also make some bar plots. You can make pie charts. You can make box and whisker plots, and all of these are really easy. It's just you're using the same ggplot command, but then you're just changing what your geometry is. And so in this case, we put geom bar instead of geom point. Or here, this is a little bit complicated because we have to start with a stacked bar plot and then change the coordinates to make it a pie chart. So it's a little bit more complicated. But you'll get all of this code, so you can use that. You can copy paste it to make a pie chart. And then this one is just for the stem and whisker plot, it's just geom box plot. You can do histogram, so let's just change this here. One thing that I think I forgot to mention is that inside your code chunk box, if there's something that you want to type and save for later, a code you want to run later, but you don't necessarily want it to run with the rest of the code, you can put that hashtag in front of it, and then that will, it'll interpret that as text and it won't run that code. So here we can make a histogram, or we can make a density plot, and here I'm just switching which I have the hashtag in front of. Oh. There we go. And then there's a really easy way to save these plots. It's just called ggSave, and you just tack that onto the end of your plot, and then you specify what you want to name it. Whoops, I didn't mean to drag that over. So in this case, this was plot 10, so we just named it plot10.pdf. You can also do JPEG or PNG file, and then just how big you want that. And you can play with that, make it however big you want it. So this is our COVID-19 model that I didn't quite have time to get to. I'm happy to keep going if that's okay, if you would want to, if everyone wants to stay and hear that. Otherwise, you'll get this in the email. I don't know, let me pause the screen sharing for a minute and we can go to the comments. Do you want me to keep going or should I just leave that for you to interpret when we send out the information? Let's see, I'm seeing, please keep going. Okay, great. Okay, we'll keep going. All right, so I'm gonna go back to sharing screen. Sorry about that. So it fit an hour, but apparently I just on and on and on. All right, so desktop, there we go. Okay, so back to our model here. Let me go back to the slides real quick. I had a couple slides just to introduce modeling. So models are getting into more of the kind of complicated meat of what you can really do with programs like R. And so basically, when you model something mathematically, you use math and logic to organize situations or events or different components and write relationships for how all of these components are related to each other. So each component itself, so this is just an example with kind of some blank little boxes. Each box here is a component. So each component has its own parameters that you input into R, and it has parameters that you can change. And so you tell R, this component has all of these parameters, and this is how they can change. And then also it shows how they're related to each other. So this component will output to this component, and it will input from this component. And you program all of that into a big function, and then you can run that. And so once you've told it what all of the components are and what they do, you can say, let these components run and do their thing for X amount of time, and then you can get a model based on how those components change over time. So let's get into that a little bit more, and I'll show you what I mean by that. So here's an example that I use when I teach about ecosystems. So this is an example of an ecosystem that we can model. And so we have all of these different components. We've got the sun, the atmosphere, the soil, and then we've got plants, herbivores, carnivores, so things are eating each other, and then detritivores, things that decompose. And so what we do is we specify, first starting with the sun, the biggest, this is how much solar energy is reaching the surface of the earth. Then plants take up a portion of that solar energy when they photosynthesize. And so we're specifying from this pool of energy that is reaching the surface of the earth, plants are taking up this proportion. Then plants are photosynthesizing using that proportion, and they're putting that into different plant materials that they're making, their leaves, their stem, their roots, things like that. They're also taking CO2 from the atmosphere, and they're putting oxygen back in the atmosphere. So they're taking some known proportion from the atmosphere, and then they're putting out some known amount of oxygen based on the plant's mass, how much plant material there is. And those are things that we are telling R, we have this much plant material, and so if we have 10 kilograms of plants, some proportion of that is oxygen from that proportion. Then we're doing the same thing with herbivores. So we have herbivores that come along and they eat some proportion of plants. So let's say herbivores are eating 10 kilograms, they're eating half of the plant mass there. And then we have carnivores that are coming along and eating those herbivores. And those animals are putting CO2 into the atmosphere at some rate. So they're putting 2 grams of CO2 into the atmosphere per kilogram of animal mass. and then they're doing the same thing. They're pulling out the oxygen as they're respiring. Then when those animals die, they're decomposed by detritivores at a rate of 3 kilograms per mass of detritivores or something like that. So we specify all of these different things, and then we allow the program to run and make this ecosystem simulation run for a year, a day, and then we get all the outputs of how these things change. So let's talk about our COVID-19 simulation. So finally, we're going to get into this example of how we flatten the curve. So real quick, I'm just going to hop back over here. So this part, I have a new heading, a new subheading here in our R Markdown file for when we get to our COVID-19 model. And so before we get into the details of the model, I've provided you a little bit of information here so you have it with the code. So this is a model. I didn't develop this. This is developed by Tim Churches, and he posted all of the code in his health data science blog. He works at a hospital in Australia. And so this uses a EPI model, or EPI model, which basically models the progression of a virus or a disease through a community. And that package was developed by Samuel Jennis and colleagues at Emory University. And it basically takes the, looks at the way that these viruses move through communities and incorporates all of that into the mathematical model. And so everything that we're seeing today, all of the different pieces of that model are just based on this epidemiology theory. So we're not actually looking at any COVID-19 data. None of this is real data. This is all just about epidemiology theory about how viruses behave and how they're transmitted from person to person within a population. So none of this is real data. So don't think that we're looking at any data. This is just a hypothetical community of 10,000 individuals and how the virus would transmit through that community based on the way that we know that viruses behave. All right, so back to our slides. So this model has 7 different components in it. So the first, and in Tim's write-up, he calls them compartments. But it's the same thing, components of the model. So the first group are susceptible individuals. And so we're specifying that we're starting off with a population of 10,000 people who all have the possibility of getting the virus. So they're all susceptible. Then we have E, the exposed and infected. So they've been exposed to the virus, they got infected with it, but they're not symptomatic. So they're asymptomatic, they don't know they're sick, but they can still get other people sick. And so that's our E component. Then we have our I component. So these are infected people, people who got sick, who are symptomatic, they know they're sick, and they can infect others. Then we've got the Q portion. So this is quarantined. So this is people who are sick, they know they're sick, they can infect others, but they stay home. So they stay home from work, they stay home from school, they don't go out into the community to spread to others. Then we have H, so that's people requiring hospitalization. R is people that were sick and have now recovered. And F is fatality, so someone who got the virus and died. And again, I just want to emphasize, none of this is real data. This is all just hypothetical, what might happen with a virus in a community. So we're not actually looking at numbers of anyone who has died. And this is how the model is put together and how all of these pieces are interrelated. So we start off with our 10,000 people being susceptible. Then from being susceptible, those people can be exposed, they can get infected, and then they can be asymptomatic. So typically you're asymptomatic, you don't know you're sick for a little while, but you can still get other people sick before you realize that you're sick. And so that's this progression here. And then we can have our people who don't know they're sick going back and interacting with the susceptible population. That's what this arrow is here. We can also have our people who are sick and know they're sick interacting with the susceptible population here. Then once they're sick and they know they're sick, there's a couple different things they can do. They can self-quarantine, so they can stay home, not go to work, not go to the grocery store, not put that virus out where they can infect others. Though there is the potential that they could still infect others there, so we do have that connection. They can infect others in their home or someone who comes in contact with them while they're staying home and not doing anything. Then they can either self-quarantine, they can require hospitalization, or they can recover. They can also self-quarantine and then come over here and recover. If they require hospitalization, they could either recover after that or they could become a fatality. And so that's how all of these components are related. And so now let's go back into RStudio and see how we actually do this. So this is kind of a complicated model, so we need a lot of different packages to be installed, and then we also need some other source files and things from Tim's GitHub. So we're just going to run this. We're not going to worry too much. We're going to let it do its thing here. So then this is just an output that we're getting all of these sources or these files that we're sourcing from the internet. And then here we get to our simulation. So this is all of the math that goes into defining each component and then defining the relationships between them. So we're not going to get into all of these different lines of code because that would be a lot, but I'll just highlight here. So this is what we're starting with initially. So we're starting with, that S component of susceptible individuals. So we're modeling this within 10,000 people, a population of 10,000, but we're going to start off with 3 of them that are infected, 3 that are sick and know they're sick. So we've got 9,997 that are healthy individuals that are potentially susceptible to getting sick, and then we have 3 that we're going to start off with sick just to run the simulation. And then all of this stuff down here is the way that these change, all of these rates of change for all of these different variables. And we're not going to talk about all of them, but there are a couple that I want to highlight. So this is the rate at which people infect others. So this is the only thing that's based on real COVID data. So this is based on observations. I think this model was written in March. So in March, the scientists looking at actual data figured out that 1 sick person will infect on average 2.5 healthy people. So 1 person with COVID will infect 2.5 healthy people. And so that's a bit of real data that is in this model. And then the other thing we're going to look at is this quarantine rate. So we're going to start off with only 1 in 30 people who are sick and know they're sick staying home. So it's often really hard to miss work or to miss school when you're sick. And so a lot of people don't necessarily stay home when they're sick. And so we're starting off with this rate of only 1 in 30 people do that. And we're going to change that in a couple of simulations as we go on. So let's just let this run. So there's a lot of code in getting this to run. And I won't go through it line by line with you, but you do have all of this information that'll be sent out to you. So if you have any questions, please just let me know. My email address, it's pretty easy to remember. It's victoria.crystal@colorado.edu because I did used to teach at the University of Colorado. I was actually just recently hired to teach Intro to Geology at Bellevue in the fall. So I will be in Bellevue. Okay, anyway, so this is kind of the sort of raw data that we get in output from this model. And this is kind of hard to interpret. We've got some really squished histograms here. So let's actually plot this in a way that is helpful to visualize. And this uses some of the same plotting tools that we just looked at earlier with our Ggplot. So there we've got our Ggplot command and our aesthetics that we're putting time on the x-axis and the count. So the number of people in each of those categories, and then we're going to color code it by category. So why don't we go ahead and run this here. And this is our plot that we get. So this is our first simulation. We're calling this our baseline simulation. So what we did was we made all of those specifications and then we let it run for 100 days. And so here on the y-axis, we have the prevalence. So again, just the number of people within that population. And then on the x-axis, we have days since the beginning of the epidemic. So initial conditions where we only had 3 people sick all the way to 100 days later. And then we've got our color codes over here. So as you can see here, our red curve is our biggest curve. So this is our COVID-19 curve. This is our infected and infectious. So people that are sick, that know they're sick and can infect others. So we have a significant number of people that are sick based on this curve. And so this is the curve, the number of sick people that we want to flatten when people talk about flattening the curve. This other curve here is orange, or I guess tan colored. That's our infected and asymptomatic. So that's people that are sick, they've been infected, but they're not physically displaying symptoms of that yet. So they don't know they're sick, but they can pass it on to others if they go to work or if they go to school. This little blue curve here is our rate this is our number of people that are self-isolating. So people that are sick and know they're sick and they're staying home. So we set that at a pretty low rate, just 1 in 30 people. So that's why that's so low. And then our little pink line here requires hospitalization, and our black line here is fatalities. So fatalities is not as high as people who are infected, but it's still, pretty significant, a couple hundred people passing away. We don't want that. We want to be able to reduce that. So let's change some of our parameters of our model. And this is how we really get to that help people determine what we do to flatten this curve. So people like governors and mayors and people in the government that are making these determinations of having people stay at home and having people social distance, they are relying on data scientists who make models like this and change the different parameters to see how we can get that red curve to go down. So let's experiment a little bit, see what we can do to reduce that. So the first thing that we can do is let's change that rate of people that are staying home when they know they're sick. So let's increase this rate from 1 in 30 people who stay home when they know they're sick to 1 in 2 people. So we're going to do this from day 15 to day 30. So right kind of early on, people are going to start staying home a lot more. So let's run this here. So then this part of the code up here is just specifying that we're changing that rate in the initial simulation that we wrote, and then we're making a new simulation called the ramp quarantine rate simulation. So we're just increasing the rate at which people stay home. And then here we go, we're gonna make a plot with it so we can see, so we're mutating some of our data. So we're pulling our baseline data and then our ramp up isolation data, and we're making a Ggplot here. Some of this code takes a long time to run just because we're telling it to do a lot of things. And so here is our comparison. I'm just gonna pop this out so we can see it a little bit better here. So this one up here is our baseline simulation. So that's what we just looked at. And then down here, this is what happens when we ramp up people who are sick staying home. So as you can see, our blue line is much, much higher here. So starting at day 15, we've increased the rate at which people stay home. So a lot more people who are sick stay home. And as you can see, we are shortening, we are flattening that red curve. So it was all the way up here and now it's way down here. So that's really good. That tells us that having everyone who's sick and know they're sick stay home really does something. That's really effective. But if we look here, we still have our orange line, are people who are sick and don't know they're sick, they're still out there infecting other people. So there is potentially something else that can be done to reduce the number of people who are sick and don't know they're sick yet from exposing other people and getting other people sick. So let's run a couple other experiments and see what we can do to flatten this curve of people who are sick and don't know they're sick spreading it. So we're gonna run 3 different experiments here. The first one is we're gonna go back and we're gonna go back to that rate of sick people staying home. So we're gonna go back to 1 in 30 people who are sick and know they're sick staying home. But then we're gonna add a social distancing component starting at day 15. So this is saying starting 15 days after we realize there's this disease going through our community, we're gonna start social distancing. So everyone that's healthy or everyone that thinks they're healthy is just gonna stay away from other people. So you're only gonna really be close to people that you're living with, and you're gonna stay pretty far away from everyone else. Just in case one of them is sick and they don't realize that they're sick, they don't have symptoms yet, we're just gonna stay away, just in case. Then we're going to do one where we start our social distancing on day 30. So instead of saying, oh no, we have some cases within our community, let's, nip this in the bud right now and start social distancing right away. This is waiting about a month until it gets really bad, until there's a lot of people that are sick. And then we're saying, okay, this is pretty serious. Let's start social distancing now. And so let's compare how those different social distancing start points affect the number of people that are sick. And then finally, our last experiment that we're going to run is where we increase that rate of sick people staying home to 1 in 2. So we're going to increase it again back to the way that we had it, and we're going to start social distancing. And so that's telling everyone who is sick, stay home, don't go to work, don't go to school, and everyone who is not sick, stay away from other people. Just in case someone is sick, you just want to stay away, prevent yourself from getting sick, or prevent yourself from getting someone else sick. Maybe you're the person who doesn't know that they're sick. So just everyone stay away. And in these models, there's not a curve that is showing that social distancing. We just have to know that it is happening because it's something that was written into that model, but there's not a curve for it. Out, so we can see that a little bit better. This top one right here, that's our baseline experiment with our really big curve of sick people. And then this is our increasing the rate of people who are sick staying home that we just looked at. And here's our 3 new experiments. So this is what happens if we keep that low rate of people staying home that know they're sick, but we start social distancing at 15 days. And so what we can see here is that we did flatten the curve a little bit. So our biggest curve is up here over 3,000 people. So we have flattened it significantly. It's not nearly this high anymore. But we still have a fair number, almost 2,000 people getting sick. And that's really not good. We don't want people to get sick. And then same with this orange curve, we still have people who are sick and don't know they're sick, potentially out there infecting other people. So let's see if some of our other simulations can further reduce that. So this is where we started social distancing at 30 days. So it was when we were just about here that we started to get almost 2,000 people were sick, that we decided, okay, we don't want, actually here at this point we had 4,000 people getting sick because we had 2,000 here in this red curve and then another 2,000 from the orange curve. But anyway, so we have 4,000 people getting sick. Let's social distance to prevent that from getting any bigger. And as you can see, we did get a significant number more people sick after we began social distancing at 30. So that was not really an effective strategy for flattening this curve. This curve is essentially the same size that it was up here in our baseline experiment, and so is our orange curve. They're both pretty similar. So that one really didn't work. So then if we look down here, this is where we start social distancing at day 15 over here, and increasing this blue line, we increase the number of people that are self-isolating, that are staying home when they're sick. And as you can see, this was very, very effective in this model of decreasing the infected people. It's down here, probably less than, maybe around 100, 200. It's really hard to tell because the scale of that plot is tough. And so this was our, based on this model, our most effective strategy here for flattening the curve, for decreasing the curve. And so this is just an example of what R can do. And so again, this is just a mathematical model, not based on any real data. But this is the type of thing that's informing all of these decisions that are being made surrounding social distancing and people staying at home. And so I wanted to include this example not only to give you a chance to have this code and to be able to play around with this, but now that you know R, you know a little bit more about data visualizing, you have all of this code, you're able to visualize your own data. I hope that that helps you to understand what people are talking about when they talk about the models, now that you can create your own model. So I really encourage you to play around with the code, Google it, go to Tim's blog. I have a link for that in the PowerPoint slides, and really now that you know how to make these models and you can visualize the data like this in R, I really encourage you to kind of think critically about some of the models that are shown on TV and things like that, and just really have fun with it now that you have kind of the baseline of information in order to be able to play around with things in R. Just do it and play around and learn more and get through that learning curve, and you'll be able to write code to make plots like this and to make models like this. And it's a really, really powerful tool that influences everything around us. Things like this model are informing policy about how we can save people's lives and keep people safe. So it's just a really powerful, amazing tool that you can do so much with. And just one more example I want to show you is you can even put in the PowerPoint slides. And so I have all of the PowerPoint slides. Oops, I got to run this code here. So this code is just loading the slides, and then this bottom code is going to put all of the slide images here into our R Markdown. And so that will be sent out for you to have and for you to keep, so you can refer to at any time. Real quick before we're over, here's our resources. So an R Markdown to writing and word processing in R. This is that YAR Pirates Guide. It's really useful. There's a lot of great information in it. Then this is our data wrangling cheat sheet. And so that just has all of the commands within the Ggplot and the tidier and the magritter in order to change up a data set, pull a column, you can flip columns and rows, great stuff like that. This data sheet is everything you can Ggplot customizations, from changing the background to making the X and Y axis titles bigger or smaller or colorful, adding legends, subtracting legends, adding annotations, really anything you could want to do with a plot, you can. And then this is the link to Tim Church's Health Data Science blog, where all of that code is for the model there. And then I used some references when I put together this presentation, and so I have that there for you as well, to see where I got some of the code that I wrote. This is a particularly useful book, R for Data Science. The whole book is actually available online. If you just Google that title, you can download the book, and that is really fantastic. With that, that's all I have. I'm gonna stop sharing. Do we have any questions or anything? Let's see. Could you email the notes and Facebook link and date for airing? Yes, we'll make sure we have all of that sent out to you. Yep, all right, yeah. I'll stick around on here for a few minutes in case anyone has questions. Yeah, thank you so much for joining, and I really hope you learned something. And please let me know if you have any questions about future use of R. Again, my email address is victoria.crystal@colorado.edu. So please feel free to email and let me know how your R adventures go. Let's see. Ron says, wow, that's fascinating stuff. Thanks. Thank you for tuning in, Ron. Yes, I believe the recording will be sent out, or I think it's available on Facebook, right? Is that, yeah, I believe the recording will either be sent out or available on Facebook. All right, doesn't look like there's any more questions coming in. So thank you everyone for joining. Really appreciate you sticking with me, even though we went a little over time. Have a great rest of your Monday and a great rest of your week. Let's see, Sarah says questions. Yeah, Sarah, do you have a question?
Hi, Victoria. She wrote something before this. She said, can her daughter email you things about paleontology? And she wants to ask some questions about those.
Oh, yes, for sure, definitely. Yeah, I'm happy to answer paleontology questions. Yeah, is her daughter here? I could show some cool fossils. I don't want to, if that's okay, I don't know. I don't want to take up Zoom capabilities, but if she would be interested, I have some fossils I could show.
Yeah, you can take some more time if you want to. We don't have any Zoom meeting until afternoon.
Okay, let me run to the other room and get the fossils. I'll be right back.
Yeah, thank you.
Okay. All right, I have a lot of really cool dinosaur fossils here. Let's see. A dinosaur that your daughter likes. Does she have a favorite dinosaur? I'll just start showing some fossils here. Let's see here. Where should we start? Let's start with everybody's favorite fossil. Does she have a favorite dinosaur? T-Rex. Ah, perfect. I just pulled a T-Rex fossil out of the bag. This is a T-Rex tooth. So this is kind of one of everyone's favorite fossils that I have. This is a T-Rex tooth. So as you can see, huge tooth. It's like the size of my face. And T-Rexes had really cool teeth. So as you can tell, it's like a little bit curved here. And that makes it particularly interesting for T-Rexes to, particularly useful for T-Rexes to tear meat. It's like if you think about when you eat ribs or something, or a steak, and you tear at it with your front teeth, having this curve makes it really easy to tear meat. And so the T-Rex could bite into the meat and then rip it really effectively with this curved tooth. The other really cool thing about T-Rexes biting things is that T-Rexes have the strongest bite strength. So just like the strength in their biting of almost every other animal that has ever lived on Earth. So T-Rexes, the pressure that they would exert from the point of their tooth is about 430,000 pounds per square inch. So PSI, so that's a unit of pressure. And just for some context of what that big number means, that is 100,000 times more pressure than a tiger bite. So a T-Rex could bite down harder 100,000 times, 100 times harder than a tiger. Isn't that crazy? Yeah, so T-Rexes just had super, super cool teeth. And they were just super cool animals, just giant, giant dinosaurs. Another giant dinosaur that I have, this is a Spinosaurus tooth. So Spinosaurus was a dinosaur that lived at the same time as the T-Rex, so during the latest part of the time of the dinosaurs, which is a time period that geologists call the Cretaceous. And but the Spinosaurus lived in Africa. And so T-Rex and Spinosaurus actually probably didn't ever meet face to face, because the Spinosaurus was in Africa and the T-Rex was in North America. And Spinosaurus, as you can see here, also had really, really big teeth. But Spinosauruses were really different than T-Rexes in where they lived and what they ate. So T-Rexes lived completely on land, and they probably ate other dinosaurs like big herbivores like Triceratops. Spinosaurs actually lived part on land and part in the water, sort of like crocodiles. So they spent a lot of their time in the water. And yeah, so they probably ate aquatic animals, so things like fish or kind of marine reptiles that lived in the water. And so Spinosaurs were really big predators, but they were completely different than T-Rex. So, and this is actually a fossil replica, so this is fake. But this is a replica of the largest Spinosaurus tooth that has ever been discovered. All right, and then I've also, so my favorite dinosaurs are herbivores. They are hadrosaurs, which are the duck-billed dinosaurs, and I love them, and they have really cool teeth too. So they were plant eaters, they were herbivores, so they didn't have big pointy teeth, but they did have really cool, ever-replacing teeth. And so we have two sets of teeth in our entire life. We have our baby teeth, and then those fall out, and we have our adult teeth. So hadrosaurs, they could have teeth fall out whenever they wanted, and more teeth would grow. So it was like they had hundreds and hundreds of sets of teeth. So their teeth would fall out, their teeth grow in, just like our baby teeth. And so their teeth actually grow in columns. So if you can see here, this is a tooth right here. This is the flat surface that I would use for chewing and grinding plant material. Like if you think about when you eat salad or something, you use those back teeth and you grind, grind, grind. And then this is a tooth directly underneath it. So when this tooth falls out, this one is already growing there to replace it. And they would have like a row of 100 teeth in their mouth. So they would have 100 of these tooth columns in their mouth. And all of those teeth were ready to fall out at any given time. They also chewed in a really awesome way, where instead of going up and down like we do, they kind of went in circles. So their jaw would kind of pop out and chew and then move back and chew and move forward and move back. So they were really cool too, even though they didn't have big pointy teeth. Sarah, does your daughter have any specific questions about dinosaurs or about T-Rex? Let's see, it looks like we've got 6 participants still in here. So does anyone in here have any questions? Yeah, Brachiosaurus? Ooh, how smart is it? That's a really tough question. That's a really good question. So that's one of the things that paleontologists are working on right now. Because the tricky thing about studying dinosaurs is that mostly we just find bones. So we don't really find any kind of soft parts of the organism. Like we very rarely find skin or hair or organs. So we don't have any fossilized brains for us to know how smart dinosaurs are. But what paleontologists are doing is that they are taking the skulls and they're running them in machines that we use today for people who are in the hospital and they're having tests run about their brain. And so we call that a CT scan. It's a, oh, what does CT stand for? Something tomography. Anyway, so that's something that we use on people to learn more about what's inside of our bodies. And so we're actually doing that with fossils too. And so we don't have a brain inside the fossil skull to look at, but we can use the CT scan to image what the brain would have looked like inside of the skull based on like the shape of the hole in the skull where the brain goes. And so we don't quite know how smart it is, but that's what paleontologists are trying to do. Since we have all of this technology, they're trying to figure out how smart dinosaurs might have been based on the size of their brains. So I can't give you a definitive answer, but I can tell you that we're working on it, and they probably, so they weren't as smart as people. They didn't have their own language, they couldn't talk, they couldn't communicate like we can, but they were probably smart in the way that some big herbivorous animals are today. So sort of like giraffes with the big long neck. They were really good at utilizing their long neck and their teeth to find food and to get food. They could definitely communicate with each other somehow. They didn't have like a spoken language, but they could definitely communicate. So they were smart in the way that animals are smart. But we don't know exactly what their brain function would have been like. So I hope that answers your question. If you're interested in that question, you can grow up and become a paleontologist and take the skulls and do the CT scans and figure that question out too. Where is the nearest place I could go dig for dinosaur fossils? Ooh. Let's see, the nearest place with dinosaurs. Probably up in North Dakota or South Dakota. Let's see, there's some fossil sites in Nebraska, but they're not dinosaurs. They're mammoths, which are much younger than dinosaurs. But mammoths are pretty cool. I would say either Colorado, kind of close, you know, if you go west enough. There's a lot of really cool dinosaur fossil locations in Colorado, or you could go up to North Dakota and Montana. So I think there's a place in North Dakota, it's not going this year, but there's, oh my gosh, I'm totally spacing what it's called. It's in Marmarth, North Dakota. It's this really small town. Oh my gosh. Oh, I can't remember what it's called. It'll come to me. Send me an email so I have your email and I can let you know. It's in Marmarth, North Dakota. It's a colleague of mine, Tyler Leeson, and it's a place where you can kind of pay to dig. So you basically like join a paleontologist crew for as long as you want, and you can go out and you can dig and you can learn all the techniques, and it's really awesome. It's really fun. I can't believe I'm spacing on the name right now. Oh my gosh, hang on, let me Google it real quick. I can't find it right now, but if you send me an email, I will definitely let you know what it's called. What? No, what's the name of the place? Yeah. Okay. Sorry that my dad just overheard. My dad has actually done that with me. My dad's come and dug up dinosaur bones with me. So he should also remember what it's called. He says he's gonna go look it up. Checking the Wikipedia page right now. Oh, it's not on there. Anyway, send me an email and I will let you know when I remember. I've just been thinking about R so much. I guess it's like R has pushed everything else out of my brain. Oh, thank you. It's the Marmarth Research Foundation. Yes, Marmarth, M-A-R-M-A-R-T-H, Marmarth Research Foundation. So I don't think they're taking anyone this year because of everything going on with COVID, but I think in the future they will definitely be taking people again. So any other questions about dinosaurs or about R? Oh, this made your day. Oh, I'm so happy. I'm glad this made your day. I love talking about dinosaurs and R. I could talk about dinosaurs all day though. So please send me an email if you think of any more questions. Thank you. Thanks for asking questions. I love talking about dinosaurs. All right, so I think that wraps it up. Yeah, anyone else?
Thank you so much, Victoria.
Yeah, thank you. What was the email address?
So it's hello@dospace.org. I'm gonna write it here.
Okay.
In the chat box. Well, I already did once, but then I'm gonna write it again.
Okay, awesome. Yeah, I'll send over the PDF and the HTML file that has the slides and all of the code and everything. So I'll send that right now so you can get that out to participants.
Yeah, thank you so much. And I'll ask my coworker to forward it to people who is going to, they want them.
Okay. Oh, and then Sarah says at Colorado in the chat, my whole email address in the chat. Let's see, I don't know why it auto capitalized it. So there it is, victoria.crystal. Let me make sure I spelled that right. Yep, that's my email address. So questions can go there, and I'll include that, I think, in the information that I send out. All right, so I'm gonna head out. I'll send that information, and yeah, do you guys need anything else from me?
No, that's all. Thank you so much, Victoria.
Okay.
I really love looking on the process.
Thank you. Yeah, I'm glad I kind of got some dinosaur stuff in there too.
Yeah, I went to Model Hall in University of Nebraska-Lincoln.
Yes, I love it there.
Yeah, it's amazing. I have been there a few times because I was at UNL, so that was nice.
Yeah, it's a great resource to have there on campus. It's fantastic.
Yeah, well, thank you so much for your session. And
yeah, thank you.
It was great talking to you. And I'll take care of all the information. If we receive any question, I'll take care of all of those.
Okay.
Thank you.
Thank you so much.
Bye.
Bye.
Bye. Have a good night.
You too.
Bye.
Bye.
Bye.